Howdy, today I'm Flippin Science looking at aldehydes versus ketones. So the science understanding we're looking at, aldehydes can be oxidized, ketones can't. Draw the structural formula of an oxidation product of an aldehyde in acidic or alkaline conditions, and describe how acidified dichromate and Tollens reagent can be used to distinguish between aldehydes and ketones. So looking at aldehydes versus ketones, the aldehydes we can oxidize easily, whereas ketones we can't. And the reason for that is on the aldehyde group there's a hydrogen here. So an aldehyde is a terminal carbonyl group. So that's the C double bond O here. There's a hydrogen here that we can change the end of the hydrogen to an OH group to make it a carboxylic acid, or a carboxylate ion, which we'll have a look at in a second. If we look at ketones, however, there's no hydrogen that we can change anything for. It's bonded to two carbons and it's a double bond to an oxygen, so we can't oxidize that readily. So the fact that ketones don't oxidize, whereas aldehydes do, we can use tests to show that and determine if something is an aldehyde or a ketone. So we can use acidified dichromate solution like we had with the primary, secondary and tertiary alcohols, but we can also use Tollens Test, and we'll look at Tollens Test a bit later on. Now, under acidic conditions, when you oxidize an aldehyde, you get a carboxylic acid. And under basic conditions, or alkaline conditions, you get a carboxylate salt, carboxylate anion. So let's have a look at how that happens. So let's talk about carboxylic acids and carboxylate ions. So carboxylic acid is a weak organic acid with the functional group COOH. So that's how we write it in condensed form, but when we draw it in structure, we have C double bond O OH. C double bond O OH, that's carboxylic acid. The double bond O comes from the carbonyl group from the aldehyde, and the OH, that's the oxidation of the aldehyde to produce the carboxylic acid group. So this whole thing here is the carboxylic acid group. The reason it's an acid is because this group can lose this hydrogen down here, and if something loses a hydrogen in the form of a proton, that makes it an acid. Acids lose protons. Well, that's one definition of an acid anyway. So how did we make this ethanoic acid? So we started with ethanol. So ethanol is a primary alcohol, so two carbons, methyl ethyl. We've got an OH group, a hydroxyl group, that's what makes it an alcohol. Then we oxidize that. We show oxidation using an arrow and square brackets with an O. Ethanol oxidizes to ethanal, so it's a primary alcohol. Primary alcohols go to aldehyde. So we go C double bond O, H, and we fill in the rest of our H's. Okay. Then if we oxidize the ethanal in acidic conditions, so we do that using square brackets, and I'm writing an H plus underneath the arrow to show that we did it under acidic conditions, you get ethanoic acid. So ethanol goes to ethanal, goes to ethanoic acid. So now if we do it under basic conditions, rather than getting ethanoic acid, we're going to get an ion instead, an ethanoate ion. So I'm going to show that again using the square brackets and an O to indicate oxidation, but this time I'm going to use OH minus. So I'm showing I'm doing it under basic conditions. So my group is going to be very similar, except we don't have the H down here. And if we're losing an H, in fact this is an H plus as a proton, we're left with an O minus. I just need to fill in the rest of my hydrogens here. So what I'm getting instead, under basic conditions, I'm getting the ethanoate ion. Now, the way we could do this is we could use something like sodium hydroxide. Now, if we do this in solution, most of the carboxylic acid will be, well, some of the carboxylic acid will be floating out as this carboxylate anion. But under basic conditions, if we remove all the water, then we're going to get our salt. So if I did this with sodium hydroxide, I would have a sodium ion sticking to the O negative of the carboxylate anion over here. And this would be our salt, so this would be sodium ethanoate, that would be its name. So if you do oxidation under acidic conditions, you get a carboxylic acid, and under basic conditions you get the carboxylate anion. So let's do some other examples of that. So we're going to oxidize this aldehyde, methyl ethyl propylbutyl, so this is butanal. I'm going to oxidize this under acidic conditions to start with. So again I'm doing a square bracket with an O, and I'm doing H plus underneath to show that I'm doing it under acidic conditions. And I'm going to make the carboxylic acid. Now I've got 1, 2, 3, 4, 1, 2, 3, 4, C double bond O, make sure it looks like an O, and then OH. I'm going to fill in the rest of my H's, and there we go. So, oxidizing methyl ethyl propabutanol under acidic conditions, I get butanoic acid. Now let's have a look at this one under basic conditions. I've got 1, 2, 3, 4, 5, 6 carbons, so this is going to be hexanal. So I'm going to show my oxidation with a square bracket in the O, and this time I'm going to use OH minus to show what's happening under basic or alkaline conditions. So I need to put in my 6 carbons, 1, 2, 3, 4, 5, 6. I need to put in my double bond O, and now I'm going to put in my carboxylic anion group. So it's just going to be O minus. Then I need to fill in the rest of my H's. Okay, so oxidizing an aldehyde under basic conditions, you get a carboxylate anion. So there are many tests that you can use to determine if a substance oxidizes or not. You can use acidified dichromate, and we've already had a look at this when we looked at primary, secondary and tertiary alcohols. So if you have an aldehyde present and you oxidize that using acidified dichromate solution, you'll get a carboxylic acid forming, and you'll also get a color change because the dichromate ion is being reduced to the chromium ions. So we get a color change from orange to green, and we can see that over here. Now it's not very clear green down here, but there is definitely a color change from the aldehyde to the carboxylic acid down here. So there is a color change in the solution. So this should be orange and this should go green, but in this case there's a bit of weird color balance going on. Now the problem with using acidified dichromate is it's a very strong oxidizing agent. So if you have any primary alcohols or secondary alcohols present, they will get oxidized as well, and that will lead to the same color change. So you get a color change from orange to green if you have an aldehyde going to a carboxylic acid, but also a primary alcohol going to an aldehyde or a secondary alcohol going to a ketone. They will give you the same color change. So you won't be able to determine between them. And the advantage of the Tollens test is it is specific to aldehydes. So let's have a look at that now. So as I was saying, the test is called the Tollens test. We use Tollens reagent, which is ammoniacal silver nitrate. If an aldehyde is present, the aldehyde reacts with the ammoniacal silver nitrate, and you get a silver mirror forming on the walls of your reaction vessel. You don't need to know the reaction equation, but you do need to know what the products of the test are. So if you have an aldehyde, you mix it with the ammoniacal silver nitrate, which is this stuff here, you get your silver forming, so that's the 2Ag here. And we can see here on the reaction vessel, in this case a test tube, we get this nice silver mirror. So you mix your mix containing the aldehyde with the ammoniacal silver nitrate. Again, you warm it for a little while because that increases the reaction rate, and you'll see a silver mirror forming on the reaction vessel. So let's have a look at Tollens test. And as always, thanks to Rees Lewis for the video. So in the conical flask here, I've got an aldehyde solution, and in that I'm adding an ammoniacal silver nitrate solution. So this is Tollens reagent up here in the beaker up here. And it's sitting on a hot plate, so it's being warmed slightly. So as it plays, we can see we're adding in, and then the video will get sped up shortly, and we'll start to see color change happening. Now the color change is a bit slow, and that's why you need to warm it up, but you can see what's happening is we're getting a darkening. Then eventually you'll start to see a real darkening on the outside. And that darkening there is the formation of the silver mirror. Now, at the end, it doesn't look particularly reflective. If we nudge towards the end a little bit, come on. It doesn't look particularly reflective, but you can see we're getting doubling up here of the graduation on the line. So if we drained this out, you would see it is quite a silver mirror. That silver mirror, that's a thin layer of solid silver, and this is how mirrors were made for a very long time. Nowadays, aluminium is used instead. Now, what you would do is you would get a piece of glass, you would coat it with formaldehyde, which is methanol, which is an aldehyde, and then you'd spray that glass coated with the methanol with Tollens reagent. You warm it up for a little bit, and then you get a thin layer of silver, and that covers the glass, and that's where you get your mirrors from. So let's have a look at some questions. So the structural formula of two monosaccharides, A and B, are shown below. Identify which one of A and B would react with Tollens reagent and state the observation that would indicate a reaction had occurred. So if we look at A is an aldehyde. At the end of the chain we've got the carbonyl group, C double bond O. If we look at B is a ketone. So we've got the carbonyl group. It's not at the end of the chain, it's in the middle of the chain somewhere. So what that means is A is going to react with Tollens reagent because it's an aldehyde, and the observation would be the formation of a silver mirror on the reaction vessel wall. So today on Flipping Science, we looked at aldehydes versus ketones. That's it for Flipping Science today. See ya.